In the previous video, we introduced Vesper theory and how it helps us predict the exact shape and structure of atoms. Today, we're going to revisit the concept of polarity and learn how it relates to molecular geometry. As a quick review, we've already defined polarity as the degree of lopsidedness observed in a bond. The more lopsided a bond is, the more polar it is. The main factor that determines polarity is the difference in electronegativities between the two atoms involved in a bond. For example, the topmost drawing here shows a nonpolar covalent bond. This type of bond occurs between two atoms that have equal or almost equal electronegativities. The middle drawing depicts a polar covalent bond, which happens between atoms that have different electronegativities, and the valence electrons involved in said bond are attracted more toward the atom with a higher En. Last but not least, we have the bottommost drawing, which shows an ionic bond. Atom 1 is significantly more electronegative than atom 2, so the electron or electrons are pulled very strongly toward atom 1 and away from atom 2. The point of all this is that bonding is essentially a spectrum and should not be viewed as a binary. The same idea applies to polarity as well. It's more accurate to talk about more polar molecules and less polar molecules, instead of juxtaposing the two as if molecules are either polar or not polar. Today, though, we're focusing our full attention on polar covalent bonds specifically. In a polar covalent bond, there's a difference in the two atoms' electronegativities, but not so large a difference as is seen on ionic bonds. Ionic bonds, of course, create ions, and ions have charges because the balance between protons and electrons inside ions is disrupted. This happens because the valence electrons in an ionic bond are attracted so strongly to the more electronegative atom that they add a full negative charge to that atom. In a polar covalent bond, the electrons are closer to the middle, but they're still being pulled more toward one atom versus the other. This unbalanced attraction adds a partial charge to each atom. We can think of partial charges as being fractions of charges. Let's look at an example to illustrate this. Here we have sodium chloride, an ionic compound. The single valence electron involved in this bond is pulled so strongly toward chlorine that chlorine gains a -1 charge. Sodium, for all intents and purposes, loses its hold on this electron, so it gets a +1 charge. But down here, we run into hydrogen fluoride, which is held together by a polar covalent bond. The single valence electron involved in this bond isn't completely at the side of fluorine, but it is leaning in that direction. So instead of granting fluorine a full -1 charge, it gets a fraction of a -1 charge. The same goes for hydrogen, but it gets a fraction of a +1 charge instead. These fractions of charges are what we refer to as partial charges, and they are only found in polar covalent molecules. Partial charges are, as can be seen in our drawing, represented by the lowercase Greek letter delta, who we became acquainted with in an earlier video. Now, polarity isn't just some obscure and abstract concept that only chemists care about. Polarity does have an impact on the overall properties of a chemical. More polar molecules and the compounds they comprise have higher melting points, boiling temperatures, and dissolve more easily in water. The reason for this is that more polar compounds are held together by stronger bonds, and stronger bonds lead to higher melting and boiling points. We'll talk about the solubility aspect of polarity in a future unit. At this point, we need to talk about what's maybe the most important topic of this video and the reason we revisited polarity in the first place. There is a relation between a molecule's polarity and its molecular structure. We can actually predict a molecule's polarity by looking at its Lewis structure, and vice versa. Before we get into that, here are 2 quick rules of thumb. Firstly, if there are any lone pairs on the central atom, the molecule is most likely a polar covalent molecule. Secondly, if the Lewis structure is not symmetrical, the molecule is probably polar. Our final point is that polarity also has an impact on the bond length. Bond length was something I thought of including in the previous video, but it's easier to combine the two concepts here. Bond length is pretty much what its name implies. It describes the distance between two atoms that are held together by a bond. A molecule with a long bond length is going to have atoms that are spread apart, and one with a short bond length is going to have atoms that are closer together. A higher bond order equals stronger attraction between the atoms, which equals a shorter bond length and a shorter distance between the covalently bonded atoms. Bond order, if we remember from last time, is how many electron pairs are involved in a bond. We ran into single bonds, double bonds, and triple bonds. Single bonds have the lowest bond order, double bonds are one step up, and triple bonds have the highest bond order. A molecule held together by a triple bond, then, is going to have its atoms closer together than one held together by a double or single bond. That's all we're trying to say here. We head now to an example problem. Example 1 would like to know if ammonia is a polar or nonpolar molecule. Feel free to pause the video if you'd like to try answering this one on your own. Let's start by drawing the Lewis structure for ammonia. There. That should be consistent with Vesper theory too. To answer this question, we need to remember our two rules of thumb. Are there any lone pairs on the central atom? It looks like we have these two electrons up here. That makes one lone pair. Just from that, we can conclude that ammonia is a polar molecule, and because nitrogen is more electronegative than hydrogen, the negative partial charge would be placed on nitrogen. Also, ammonia is actually asymmetrical in its structure. It's a bit hard to show this using a two-dimensional drawing like this one, but if you look up examples of 3D structures of ammonia that people have built, we will see that it isn't possible to draw a line of symmetry anywhere on this molecular structure. Example 2 is asking if water is polar or nonpolar. This is the Lewis structure for water, and again, this should be consistent with Vesper theory. Water is kind of a strange case, and this is kind of a trick question, because water is in fact symmetrical. We can see that just by glancing at this drawing. But because of these two lone pairs on oxygen, and the difference in electronegativity between oxygen and hydrogen according to the Pauling scale, we have to say that water is a polar molecule. The main reason why this example problem is included is to illustrate the point that these rules of thumb are only general guidelines. The best way to know for sure whether a covalent bond is nonpolar or polar is to look at the two elements involved and use the Pauling scales to calculate the difference in their electronegativity values. As a quick aside, the polarity of water actually plays a huge role in a lot of its unique properties, and we'll talk about this more in the near future. Like last time, we're going to end on a more conceptual note. Example 3 says, a covalent bond between atoms of the same element will always be blank. The answer is nonpolar. The reasoning behind this is simple. Two atoms of the same element are always going to have the exact same electronegativity. This means that the electron or electrons they share aren't going to be pulled toward one atom over the other, and that is the very definition of a nonpolar covalent bond. In the next video, Unit 2, Video 7, we're going to introduce hydrogen bonding. Thank you for watching.